Okay, exam 3-1D by Callie Cole, prokaryotic replication forks. Okay, so we're going to start down here. This is our prokaryotic DNA. And then this is the replication bubble, which we're going to look at with more in detailed look. Let me zoom out to here. So as you can see, we have the parent strand at the top, which is 5' to 3', and the parent strand at the bottom from 3' to 5'. These are originally connected, but then helicase is the enzyme that essentially unzips the double helix by breaking down the hydrogen bonds to separate or keep the two together. And then back here we have gyrase, which is also known as topoisomerase. It's the enzyme that reduces the tension or torsional strain that the DNA experiences and builds up from unwinding and supercoiling. And then once those two strands have been separated, these single strand binding proteins attach on, and they're what keep the DNA from recombining so that you're actually able to have a template for your replication. And as you can see, we have two different strands that are being created: the leading strand, which goes from 5' to 3' always, and the lagging strand, which is down here. So since we always go from 5' to 3', it's not able to head towards the replication fork, which is down here in that direction. And so it, to solve this, it creates Okazaki fragments that are stacked up and combined to make one continuous strand. That's done with the help of RNA primase, which is an enzyme that puts these primers here into place that essentially copy the DNA sequence into an RNA sequence, and that way it can be copied. And then DNA polymerase comes back in and replaces the RNA primers that are here, or would be on the end of the Okazaki fragments, with DNA nucleotides. And then once that's done, they continue to line up. And then to have one continuous strand instead of all these fragments, ligase comes in and is the enzyme that puts them all together, so that we have the second continuous strand of replicated DNA.